For example 2 from this chapter 4 on stability, here we have a third order differential equation, which is representing the dynamics of our system, and we want to determine the stability. So I failed to write down our goal here, so let me write it up here at the top that we want to find the stability of this system for small initial conditions about equilibrium. So our differential equation is as that. What I would do is take the Laplace transform of that thing, put in our arbitrary set of initial conditions. I have an s squared times the initial value for y. I have an s times initial condition for y dot, initial condition for y double dot. I have a minus s initial condition for y, minus y dot initially, plus 6 times the initial condition for y. That's all the stuff at the top. To be honest, we don't really care about the precise form of it. What we're really interested in here is the denominator d, s cubed minus s squared plus 6s, and that's what we've been calling d of s. We know it's the poles, the roots of ds, that are important. So to find the poles, we set d equal to a 0. That's a third order polynomial in s. It's really not all that hard to solve. We factor out an s from this. We get s squared minus s plus 6. Again, we're looking for the roots, so that's a 0. So therefore our first pole, P1, is a 0. The other two roots, P2 and P3, I use a quadratic equation. I get plus 1 plus or minus 1 squared minus 4 times 6 divided by 2. So our two non-zero poles here are plus, I'll put the plus in front because that's really important, plus or minus j times the square root of 23 divided by 2. The important result, well, we have complex poles, that's for sure, and they have positive real parts. So we're really focusing in on this sign here. That is what sort of tells us a lot about the stability. So if we invert our y of s, we realize we have distinct roots, so we can say that y of s then can be equal to a1 divided by s minus p1. I have an a2 s minus p2. P3 is a complex conjugate of P3, so that's going to give us A2 bar divided by S minus P2 bar. And so we know this ends up giving us 2 times the real part of A2 over S minus P2, and we know right away what that's going to be. Whenever we do our inverse Laplace transform, we get an A1. Well, keep in mind here that P1 just ended up being a 0. It had a 0 root, so we just got an A1 here. And then what we get from this is 2 times the real part of A2 E P2T. And as we've done a number of times in this course up to this point, this is going to end up being 2 times e to the 1/2 t over 2, all times some coefficient a, which we won't bother define because that's not really what we're interested in. Likewise, here for sine, we got a b sine square root of 23 over 2t. So right away we see this. This is an unstable contribution. You start out the system with small initial conditions away from equilibrium, and they don't come back. But this instability is different than the one from example 1 in that what we have for just this contribution here is something that looks like this. Some perturbation has it going away with an exponential growth on the amplitudes of the oscillations.